Alright folks, we're going to do a relatively short video today introducing thunderstorms and tornadoes, and we will jump back into this on Monday, and then we will actually end up finishing this off after our spring break this semester. And so a little bit of motivation as we jump into today's video. On a side note, take a look at, if you have a couple moments, at what happened over the southeast on Thursday. As I put this video together about 5 o'clock in the afternoon on Thursday, pretty good regional outbreak occurring. Definitely went high risk again, and there's been a couple of significant tornadoes near the Birmingham, Alabama area. If we get a chance on Monday, I'll bring up a little bit about this as well. And so here we're simply looking for what is needed to create a thunderstorm. We've brought a lot of the individual pieces together, such as mid-latitude cyclones and fronts, and talked about stability, but we're really going to kind of put this recipe together and talk about what for general thunderstorms as well as severe thunderstorms. We're going to talk about different types of thunderstorms. This video is going to talk about the single cell thunderstorm, and then next week and further on we're going to work our way through multi-cells and supercells as we work into tornadoes and the like. And let's be honest, probably more than 30-40% of you are in this class because you figured, hey, it'd be kind of cool to learn about thunderstorms. So we're going to learn about that. And tornadoes, they're obviously very impactful. They're causing some significant issues today over the southeast, and more than likely we'll see some incidents here in Valpo as we move later into the spring and early summer months. And so we look first at this map of thunderstorm days. The idea of a thunderstorm day is simply a day in which a thunderstorm is experienced. And so the idea is that you can have a thunderstorm over your head for 24 hours or for 5 minutes, and it's going to count as one thunderstorm day. And so you can see a couple of interesting things that pop out. You see first and foremost what I have circled there with the word Y. Florida sticks out like a sore thumb. Here again, think of the land-sea breeze, that convergence that happens regularly over a number of the spring, summer, even fall months. And that's going to produce basically 1 out of 4 days over portions of south central Florida that are going to experience a thunderstorm. And overall, you can see in general, we see the southeastern United States experiencing the most thunderstorm days. And this goes back to the idea of maritime tropical air masses, warm, moist air. That is going to be one of our key ingredients for thunderstorms to be able to develop. You can notice a little bit of an interesting feature across Colorado, where we have that upslope component, helping to produce thunderstorms in the lee of the Rockies. But a couple other things stick out. You see northeast United States, pretty low number of thunderstorm days, in large part because you're getting separated from that warm, moist air mass. And then especially as you go into the western United States, west of the Rockies, simply don't have the necessary moisture in the air regularly to be able to produce thunderstorms. And so if you are listening to this and thinking, I hate thunderstorms, Central California may be the place for you. And so what are the ingredients that we need for a convective thunderstorm? Convective, these bubbles of rising motion. And when we talk about a thunderstorm, we're effectively just talking about a cell or a line, basically some type of component that has thunder and lightning. And when we look for thunder and lightning, we're usually going to experience this with warm air that's rising within a conditionally unstable atmosphere. And so hopefully the concept of conditionally unstable is still fresh in your minds as you're viewing this video. Do we get enough oomph to break through the lower stable layers to get into a section of the atmosphere higher up that's unstable and is going to help us to produce our deeper cumulonimbus clouds? We'll talk later on about what produces thunder and lightning. Basically, we're separating the charges, the protons and electrons that are within a thunderstorm, and that's going to be effectively done through a lot of rising motion and the production of things such as hail. And so the 3 key ingredients, stuff that you need to know, not necessarily for the second midterm, but when we get around to that third midterm. So again, to be a little bit of an extra reminder, this is not part of next week's midterm exam. Moisture, instability, and lift. Again, moisture, instability, and lift. So the first one there, humidity and moisture. This is why the southeast is going to have the large number of thunderstorm days. That maritime tropical air mass, that warm air able to hold more moisture, greater capacity, and therefore we're going to see a greater proclivity to see thunderstorms where we have the available moisture. Conditional instability, basically we need a layer of the atmosphere in which these thunderstorms can grow vertically. And that's going to be something that is more common within a maritime tropical air mass, but often we're going to look for that cold air loft. Think back to the slides on stability and what we can do to make the atmosphere more unstable. And finally, a source of lift. frontal boundaries, convergence, orographic lifting, a number of ways that we can get air to rise within the atmosphere at any time. And so we're going to talk a little bit about the idea of a single cell thunderstorm. And since the bullets are a little off, let's just go ahead and put it all up there. When we talk about a single cell thunderstorm, we're talking about a coupling of an updraft and a downdraft. Updraft, rising air in a thunderstorm. Downdraft, sinking air in a thunderstorm. And this is going to be the most basic component of a thunderstorm. We're going to talk about single cells. We're going to talk about a number of these in conjunction, as I said, multi-cells, and then sometimes these can develop into long-lived features called supercells. But the single cell thunderstorm in and of itself lasts about 30, maybe 45 minutes to be perfectly fair. We're going to talk about the stages of the life cycle in the upcoming slides. And these are going to be the types of thunderstorms that develop in regions that have enough instability to form a thunderstorm, but not a ton of instability, not like what we're seeing here on Thursday across the southeastern United States. And also shear. Shear we haven't talked about yet, and will come up and we'll spend more time on it when we talk about supercells and the like. The idea that shear is going to be a fourth ingredient on top of moisture, lift, and instability when we're looking for severe weather to form. And so there are other terms for the single cell thunderstorm. Ordinary cell. A lot of people will call these air mass thunderstorms. This is the type of feature that, again, when we move into May, June, July, you'll just see by mid-afternoon over the southeastern United States, these cumulonimbus clouds popping up, and we start to see these cells developing in what seems to often be a random type fashion. Just enough instability, just enough lift, and we can get these cells to develop. And so you can see here the three stages, which we'll break down in the next few slides to finish off today's video. And we have our cumulus stage, the mature stage, and the dissipating stage. And so you can see first one, not a lot going on. Middle one is going to look like our most mature thunderstorm, thus why we call it the mature stage, and that poor little house about to get struck by lightning. And then once the downdraft or sinking air dominates, it effectively turns the single cell thunderstorm into a dissipating stage. The idea again that this is going to happen within a relatively short amount of time, the entire life cycle of a single cell thunderstorm. And so let's start with the cumulus stage. Cumulus stage is going to be when we get enough rising motion, this low-level convection, and maybe there's a frontal boundary, maybe there is some topography helping to lift the air. Sometimes simply surface heating. The hot time of the day is going to be when we can start to form these cumulus clouds. And we're getting it to where this is the updraft only. That is the real identifying factor of the cumulus stage. We'll see that as we move into the mature stage, that's when we start to pair the downdraft. And so as we have this rising air, we rise up to that convective condensation level, that CCL that we talked about with instability. And this is going to start to form a cloud, condensation of our vapor, and that latent heat release. In fact, you can kind of even look at this graphic and think, all right, we got the dry adiabatic lapse rate all the way up to the base of this cloud before our parcels start to cool at the moist adiabatic lapse rate. And so at this point, there's no precipitation going on yet. Rising air is not going to actually cause precipitation to hit the ground, but as these parcels rise higher and higher, the cloud gets larger and larger, we can start to form cloud droplets that merge. We'll get more into precipitation processes later in the semester, but you can also see that in this schematic, we're getting some temperatures below freezing, and that is one of the things that is sometimes critical to produce thunder and lightning. Mature stage is when we effectively are now pairing things with that downdraft, and precipitation begins to reach the ground. You can still see our updraft on the left side of our schematic here. The red arrows rising up into the cloud and spreading out at higher and higher levels. But alongside it, we now have blue sinking arrows. And the red is to try and show this is that warm air rising, and the blue is to show that there's precipitation, cooled air sinking. And so you can even see these cold air that as it hits the ground, that more dense cold air spreads outward. And so you can see features referred to as gust fronts. We'll talk a little bit more about gust fronts as we talk about severe weather later on as well, because these can be where we get some strong winds. And again, we'll get more into the details of what actually causes our lightning to occur and why some clouds, or some storms, if I should say, produce a lot of lightning, whereas some may produce very little. entrainment occurs. We start to bring some dry air into our thunderstorm. So not that it's weakening instantaneously, but you are going to start to see the storm weaken pretty quickly, actually, after we enter the mature stage, not unlike a mid-latitude cyclone. And so we may see an anvil cloud. If you've ever, played some video game or watched something on the History Channel and you see a blacksmith's anvil. This idea that we have the air reaching up all the way near our tropopause and spreading out as it hits a stable layer and has trouble going up any higher in the atmosphere. And so we basically end off things here with the mature stage. Mature stage. We got the gust front, talking a little bit more about this here. We see a schematic of a supercell where we get this downdraft cooled air that spreads out further and further ahead of what's going on in our thunderstorm. And this cold air pushes outward, we can sometimes start to cut off the warm air, and we'll see that on the next slide. And so the leading edge of this downdraft air can form this gust front, where you sometimes see these pretty scary looking cloud formations. I'll take a little bit of self-credit for putting this image together. Looks menacing and sometimes produces some pretty strong winds as this cold air moves out ahead of the storm. And when you experience a gust front, you'll usually see this type of cloud feature coming in and gets really cold as it moves through, and then the precip forms behind it. And now I got ahead of myself on the last one. We get to the dissipating stage. That rain-cooled air effectively has cut off the updraft. And so those red arrows in the mature stage and even back in the developmental stages, those are fueling the storm. We need that warm, moist air as the energy for our storm. And so as the rain-cooled air sinks within our thunderstorm throughout the mature stage, that gust front moves out ahead of a storm, it makes it really hard to continue to feed our thunderstorm with warm, moist air. And that's one of the ingredients we need. And so once it's cut off, we start to dissipate. Downdraft only. That cool outflow air has effectively ended our updraft, and so this is going to be when we may still get a little bit of heavy rain, but the thunderstorm, for lack of a better term, kind of rains itself out. And so you can see in this example, not a lot of cloud even at the base, just a little bit of an anvil left over. And again, remember this entire process, 30-45 minutes is what it's going to take. 12 minutes, told you we keep it short today. Have a good one, and we'll see you on Monday.